time. So the goal here is to look at non-interacting system and to compute the entanglement spectrum for these non-interacting systems. And the most simple example of a topological phase, non-interacting topological phase, is the integer quantum Hall effect. So I remind you the edge of the integer quantum Hall effect, which is just a chiral edge mode. And I've shown you last time how to, once you know the dispersion relation for the chiral edge mode, how you build from this the many-body energy spectrum for your edge. And I've shown you that basically, if you do this calculation, you should get one state at energy, at your reference energy, then another state at the energy which was like a times integer, some constant, then 2 states, 3 states, 5 states, and so on. So this counting is actually a signature of the chiral edge state. Now we have to consider the bulk wave function of the integer quantum Hall effect. And now I think you have seen this one many times. So this is the usual expression for the bulk wave function, the many-body wave function for the integer quantum Hall effects, just the product Zi minus Zj times the Gaussian weight. If you're used to occupation number, basically it means that all the orbitals from momentum 0, in this example, to up to momentum 8, all the orbitals are occupied. Remember that the one-body wave function is just the Z to the power m if you take the symmetric gauge. And if you want to write the wave function in second quantized notation, it's just the product over all the creation operators from 0 to the last occupied orbital. Okay, so what we want to do is to compute the entanglement spectrum when we cut the system in real space. So let me just give you the general technique to do such a calculation. So imagine you cut your system into 2 parts, A and B. And let's say C dagger is a creation operator associated to one orbital. So that's the wave function in real space, and that's just the creation operator corresponding to this orbital. So what we want to do is to say, okay, we want to split this creation operator onto the creation operator where the particle is only in A, and the creation operator where the particle is only in B. A, here, particle is in B. Okay, alpha and beta are just constant here. And if you want these creation operators, C dagger A, and C dagger B, to be creation operator for fermions, they should satisfy the usual algebra for. So C dagger has to be, the anticommutator has to be equal to 1. Same story for these two guys. CA dagger, the anticommutator should be equal to the one of CB dagger, and equal to 1. So from this, you show that the norm of alpha to the square plus the norm to beta to the square has to be equal to 1. Good. So now let's look at the wave function. Well, we can always rewrite the wave function this way. Theta A of R times phi r plus 1 minus theta a of r phi of r. Right? This is the Heaviside wave function where it's equal to 1 if r is in A. And 0 if you're outside A. Yep.
When you do this separation, I mean, I suppose that CA and CB or CB dagger are identical.
Yeah.
Isn't there a problem in the counting of states at the end of the day? I mean, it seems as if you have doubled, so to say, each of your states.
No, you still have the same number of particles because the particle is either in A or in B.
I mean, I see it from the wave.
Yeah.
But I mean, if I count now this numbers of states that are associated with the creation operators and elimination operators, it looks as if it were doubled.
No, because you will define a basis for what's going on in A and what's going on in B. So that's exactly what you do when you separate your wave function into a part that live in A and parts that live in B. No. Maybe let me show you the... So we're going to define two wave function. One that has that lives only in A. And we'll call this one NA times phi A, which is equal to this theta A of R phi R. So the NA and NB are just normalization factor. We want the phi A and the phi B wave functions to be properly normalized when you integrate over A or if you integrate over B. Right? You want the integral over A dr of phi A of R to be equal to 1. So this tells you that NA has to be equal to square root of over A dr of the original, the full wave function. And you can do exactly the same kind of calculation for phi B of R equal to 1, so this gives you the normalization factor NB. And you can notice that if you take NA square plus NB square, you get 1. Okay, if you sum the normalization factor for phi A to the square and normalization of phi B, the coefficient NB to the square, you get the normalization of phi over the entire space, which gives you 1. Okay, so now I'm almost done because by definition, if I create one electron in phi r, so this is the expression of the wave function. I can use this formula here, and I will get that alpha r CA dagger plus beta r CB dagger has to be equal to phi r. This is by definition the wave function of my system, but restricted to A. So this is phi A of r. Same story here. That's the wave function restricted to B. So this is phi B. So
there should be a half, right? NA squared plus NB squared over 2 is 1.
Over 2. No. Look, if you take the square, you get the sum over, you have the integral over A plus the integral over B, which is the integral over the full space. So that's, and since your wave function phi r is normalized over the full space, this is how you recover the 1. Right? The wave function phi A, it lives only in A. I agree with you if you know a little bit about the story of the spectrum. In some cases, you will have a 1/2 factor, but it means that you take a wave function that has support over the full space in that case. You decompose into A and B. Okay. So just by comparing this formula here and this one, you get that alpha is equal to NA and beta is equal to NB. So we have a generic way to decompose when you look at one orbital and you want to do the real space cut. We have to divide the system into a part A. So we need a wave function properly normalized on A and another wave function properly normalized on B, such that when you create a particle in the full system, it is either in A or B. Good. So far so good. We can now do the calculation for the integer quantum Hall effect. Because what we have done here for a single orbital, we can do that for all the phi m. So back to the integer quantum Hall effect. Yep.
So if I create a particle in A, say, isn't it a huge number level mixing if I take some orbital?
Right. Because if you make a sharp cut, of course, as an orbital, to make a sharp cut with a given momentum, you need to make a combination of all the states, all the Landau levels with a given momentum. So that's right. If you focus on, of course, on a single Landau level, then you cannot localize your wave function accurately. So there's no way you can make a sharp cut. Okay, so we want to cut the system, but we want to do that in a smart way. By smart way, I mean that we want to keep good quantum numbers. Right? Of course, you can take any shape for A, but then the calculation will be very, very messy. So since we use here the symmetric gauge, we will make a cut which is just a circle. So imagine you have the origin of your system, and you make a circle of radius r. So this will be inside the circle, this will be A, and the rest of the system will be just B. So we preserve the rotation symmetry. So it means that the calculation that we have done for a single orbital, we can do that for each of them without Z. Wait. right? It's just exactly the formula that you have here, maybe written not in a nice way, but for each orbital. And this is true because the way we cut the system, we preserve the symmetry, right? Otherwise, you would have to involve all the momenta at the same time. And well, more precisely, your angular momentum won't be a quantum quantity here. So phi AM and phi BM or MB. Should use a proper notation. And also eigenstates of LZ. And the angular momentum is so as usual, let's do a simple calculation. Don't start with the wave function with 200 particles. So one we already know the results, right? This is this wave function, this decomposition here. So let's look at 2 electrons. So the wave function, the integer quantum Hall effect wave function, if you write it in second quantized notation, it's just C dagger 0. You occupy the orbital with the lowest angular momentum, and you also occupy the next orbital with the LZ equal to 1. And now, for each of these for these 2 creation operators, you apply this decomposition here. So the first one is Na 0, C dagger A 0 plus NB 0, C dagger A 0. Same story for C dagger 1. So you have Na 1, C dagger A 1 plus Na NB 1, Ca B 1. Now I can expand this product here. We get Na, what's Na 0, Na 1, C0, Ca 0, C dagger A1 plus its twin brother CB1, CB0, and B1, C dagger B0, C dagger B1, 0, plus 2 terms, Na0, NB1, C dagger A0, C dagger B1, minus Na1 and B0, C dagger A1, C dagger B0. Yeah?
It's because of the special choice of the edge that you can commute A and B.
They anti-commute. They're not in the same space. So they are Fermi operators that anti-commute. That's it. Okay, so now let's look at this. Once we have written down this product, developed this product, we have three terms. So the first one, it's two creation operator in A, right? So this is the part where we have two particles in A. This one, you have two particles in B, and here you have one particle in A, one particle in B. So as you see here, this is a wave function that lives only in A. So if you want, it's a wave function, let's call it whatever, 0 tensor product, the vacuum for B. This one will be like a wave function, the vacuum for A, tensor product, a wave function that is only in B. And there you have actually the product of, so let me do that properly. I should use another label than this one, but it's right. So what you have done here is just the Schmidt decomposition of your states if you cut your system into A and B. So from the Schmidt decomposition, we can directly read out the entanglement spectrum. The entanglement spectrum will have four terms: this one, this one, this one, and this one. As usual, when you have entanglement spectrum, the first question to ask, or the way you should compute the entanglement spectrum, is first, what are the good quantum numbers here? So we already know that LZ is a good quantum number. So in principle, I can plot the entanglement spectrum by looking at how many values I have per LZ sector. But actually, there is another there is another quantum number that's be used to label all the levels in your entanglement spectrum, which is namely the number of particles. N. The number of particles, the sum of the number of particles in A plus the number of particles in B. Right, so this is one quantum number. The other one is LZ, which is LZA plus LZB. Now, what about the entanglement spectrum for my problem? When the number of particles in A is 2, and B is equal to 0, and this is this situation here. So we have a single state with LZA equal to 1, and its value is just, remember, for the Schmidt, the way that you have in the Schmidt decomposition are just the square root of the eigenvalues of the reducency matrix. So it's going to be minus log of NA0, NA1 to the square. So that's the first eigenvalue. The other simple case is when the two particles are in B. If NB is equal to 2, then NA is equal to 0. And of course, LZA is equal to 0. And you have a single eigenvalue, which is log of NB0 square and B1 square. Now when you have one particle in A, you have two options. You have this state here, the value of LZA for this one is just 0. Right? It's just you create one particle in A with the angular momentum 0. So there is one state at LZA equal to 0, which is minus log of NA0 square and B1 square. And the next one is NA equal to 1, LZA equal to 1, which will be NA 1 square and B0 square. This is this part of the Schmidt decomposition. There is a single particle in A. Its momentum is 1. So LZA is equal to 1. So the entanglement spectrum for the integer quantum Hall effect for two particles, if you look at all the sectors, all the possible quantum numbers, you have only 4 levels, and here they are. Here are the values. Exactly. Yeah?
Is there any way to see that these numbers are gauge independent? Because you heavily relies on the gauges you chose. I can take one double gauge of probably get different numbers.
It's going to be quite tricky because you see that the gauge we have, it's not only the gauge that we have fixed, we have also fixed the way we cut the system. So in principle, you're right that if I change the gauge,
you will have to cut it differently.
Yeah.
Probably the numbers will
Yeah, exactly. Well, if you don't change the geometry, if it's exactly the same problem, you should get exactly the same numbers. Now, of course, you won't have, you will still have the NA, the number of particles, a good quantum number, but you will lose information about LZ. Right? But like, for example, it's, if you think about how many states you should get, you can always sum up over all the LZ sector. So even if you screw up the rotation symmetry by your calculation, which is nothing like, not disorder, it's just a gauge choice, still the number of levels will be exactly the same, the energy will be the same, but you don't have this resolution in terms of LZ. But in principle, the calculation is doable. If you move away, let's say, not for the integer quantum Hall effect, but for interacting system, where it's not exactly Moller wave function, but like some exact ground state coming from numerics. And if you have an entanglement gap, even if you lose the resolution on LZ, you will still be able to find the gap in your entanglement spectrum. But the direct answer is there a simple way to see that you should get exactly the same number if I change the gauge? I don't know. I've never tried. It's already quite painful to compute this coefficient using the gauge, which is specially chosen to be compatible with the way you get your system. So I didn't try to use like the Landau gauge for that.
So try to say that for every gauge choice, there's just one logical way to pass the system, because wave function is localized only in one direction. In this case, it's radial.
Right. Imagine now if you do the same calculation not on the plane but on a cylinder, for example, then of course I won't using a symmetric gauge on a cylinder will be like a nightmare. So I will use the Landau gauge, and the calculation will be also quite simple in that case. I will have K as the momentum as a good quantum number, and I can do the same kind of calculation. So this is like the natural gauge that you will choose for that kind of cut, like cutting the cylinder into two. Yeah.
Perhaps just a possible answer to this question is, I mean, here you don't think too much in terms of gauge. You just have a set of a basis set of wave functions. Okay, so instead of saying I changed the gauge, you just say I changed a set of basis wave functions. So, and actually they are related by unitary transformation without changing the energy. But now you need to express your good quantum numbers in the other gauge. And this is a formidable problem. It is as if you wanted to write an Lafrance wave function in the Landau gauge. It is possible. There is a one-to-one correspondence. It's just not adapted. You use them, so to say, the wave functions or the basis that is best adapted to your problem.
Okay, the answer that you get is the same, or not?
I think people have tried to do it with Lafrance wave functions, just to write it down. And I don't know whether they have really managed to do so.
My point is that as long as you cut in the same way, there is no reason you think you will get exactly the same spectrum. And as long as you won't get the resolution in LZA. You use a different basis also for A and B, right? So, but then your result should not depend on the basis that you pick, as long as it describes exactly the same physical system. But I've never seen people doing that kind of calculation. It's an interesting question, but yeah. Okay, so it was for 2 particles. So let's do 100. It's going to be super boring. No, actually, it's going to be painful for me, so I will just give you the formula, the generic one. But the idea is exactly the same than for 2 particles. So don't be afraid by the formula. It's exactly the same spirit. So first, if you write down the Schmidt decomposition of your state, you know that you will have contribution where you have NA particles and NB, right? So NA can go from 0 particles in A, up to the total number of particles, N. Like in the previous example, we went from 0 to 2. So that's why we have the sum over NA from 0 to N. Remember the Schmidt decomposition, you have of your state I exponential of psi I over 2 AI tensor product BI, right? With AI AJ is equal to BI BJ delta IJ. Then you sum over all the LZA sectors. Right? Like in this example, even if we fix NA equal to 1, we still have 2 options for LZA. You can go from 0 to 1. You can do the same, so it would be exactly the same story for the general case. And there, if you look carefully what we have done here, we said, well, we have 2 options. We have 1 particle in A. It can be in orbital 0 or in orbital 1. So the generic formula, you will have to specify, well, the particle 1 is in orbital LZ A1, the particle 2 is in orbital LZ A2, blah, 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 up to LZ N. So this is the total angular momentum. For A, this is like 1 occupation number. If you remember my story with boxes, it won't be M. I've called this one LZA. And I will say, well, I have like 1 particle at LZA equal to 0. I have 0 particle in 1, 2. I have 1 particle in LZ equal 3, 4, and whatever. 6, 7, 8. So this example is for NA equal 1, 2, 3, 5. And total LZA is equal to 3 plus 4, 7, 14, 22, if I'm not completely drunk. So please check. So you have to sum over all the configuration, all the possible way to put NA particle in the original number of boxes, so the original number of orbitals, and such that the total angular momentum is LZA. Everybody is fine with this one? Okay? Now the prefactor. We've got LZA. Oh, it's called NA, my notation. NA. LZA I equal to 1. to NA product CBI, and then I have two many body states. CAI. So I need to define what is the LZB. Well, so if I choose this configuration for LZA, for the A part, then I know what are the angular momenta for the B part. So that's LZB. And I have NB is equal to 1, 2, 3, 4 particles. And LZB is equal to 1 plus 2, 3, 5, 8, 8 plus 6, 14. And you can check that compared to this configuration here, of course, Na plus Nb is equal to 9, the original number of particles that we have here. And that the angular momentum for this guy here, which is, it's 8 plus 9 divided by 2, so it's, help me, 36, 22 plus 14, 46, it's 36. Good. So far, so good. So this is the way you define the configuration for the B part, right? Where you have a 1 for A, you put a 0, and when you have a 0 for the A, you put a 1. You can check that, of course, two configurations, if they are not identical, they are orthogonal. So they really satisfy the Schmidt decomposition. So here we go. You have the Schmidt decomposition of the integer quantum Hall effect for any number of particles. Okay. Up to some minor details, if you want to be really careful, there might be a global minus sign because you have to do some reordering. Here we impose that to have all the creation operator for A and all the creation operator for B. So you might have to do some anti-commutation to end up with such a formula.
Sorry?
Yep.
Shouldn't there be somehow an anybody? Or do you include it in the ends?
You mean like combinatorial factor or just the NA factorial and...
Yeah, like if I would just expand psi the odds, there would be some psi which is going to all the angular momentum odds. Some number for each configuration.
Yeah, you have one thing I didn't do here, which if I want to be do the calculation really exactly, you have of course to include the normalization factor for the many wave function and for your basis here, right? So there is a 1 over square root of NA factorial here and here.
Oh yeah, sure, but I mean, so the NAs that we get, are those exactly the same as these orbits that we...
Yeah, that's the one body. It comes only from the one body configuration, one body wave function.
Okay.
Right? Remember, at some point we are decomposing for any m into phi am and phi bm with two coefficients which were the NAM and NBM. These are these coefficients
but
here.
Then where's the many-body information of this wave function?
Well, it's a many-body wave function.
Yeah, but it's not a generic one.
No, I mean, I do the calculation for the integer quantum Hall effect.
Oh, okay.
If you want to do the same calculation for a true many-body wave function, not a single zeta determinant, it's not doable by hand. You have to use a computer for that. Good. So let's now focus on a particular sector of the entanglement spectrum. So we have all the eigenvalues of the reduced density matrix. You can just read them out from the Schmidt decomposition. And So focus on the entanglement spectrum. Let's say with half of the number of particles of the original system. So if you want, you focus on a single block of your reduced density matrix, the one where the quantum number Na is equal to n over 2. Okay, so if you do the calculation, there is a minimal value for the total angular momentum, which is Na minus 1 divided by 2. Right? Just that if you think about the occupation number, and you keep, let's say, 5 particles. Let's take n equal to 10, n equal 5. So in this sum here, the smallest angular momentum that you can create is basically to put all your electrons to the left. And there is a single way to do that. So you will get a single level. Okay, now let's move on to the next case. As you'll see, this is at LZA min, and this is LZA min plus 1. Once again, if I want to look at the configuration that has an angular momentum increased by 1 unit, there's a single configuration that can do that. Basically, I can only move this guy here to the next orbital. So you have a single state. You repeat the exercise, and actually, if you remember how we built the many-body energy spectrum for the edge state, it's exactly the same exercise. So the next one, you have 2 states. You can count them if you want. Still have 3 boxes, or one, 0, 1, 1, 0, 0, 0, 0. That's LZA min plus 2. Next LZS sector, you have 3 states. Next one, you have 5. So 1, 1, 2, 3, 5. So you find back exactly the same counting that the many-body energy spectrum for the edge of the integer quantum Hall effect. Of course, here what I didn't do is to, you have to compute the energies and see that the entanglement energies also increase almost linearly with the LZA. You have to be careful. This is not true in finite size. Of course, in finite size, at some point you will also deviate from this counting. Basically, as soon as you involve some particles here, when you move them to count how many states I have, there will be some difference between the counting of the edge mode and the counting in finite size. The finite size also, the states are not exactly degenerate. Remember, for the edge spectrum, the true energy edge spectrum, all the states are exactly degenerate. This is not the case when you do a finite size calculation, but still, if you go to very large system sizes for the real space, the spectrum of the integer quantum Hall effect, you will find almost a linear slope. All the states exactly degenerate with the proper counting. So, the entanglement spectrum, when you do a real space cut in real space for the integer quantum Mole effect, you find back exactly the edge, the energy spectrum of the edge mode of the integer quantum Mole effect.
So
Yep.
why?
Yeah.
Why these two things are related?
Why this would?
Besides the comparing of integers.
Well, that's the idea that basically, when you cut your system in this topological phase, you know that everything should happen at the edge. So somehow it's not surprising that the energy spectrum of the different weights mimic what's going on at the edge. Maybe a more precise way to think about it. So first, you can say, okay, but you're looking at a specific sector of the entanglement spectrum. You fix the number of particles to be n over 2. So first, if you have a large system, it doesn't matter. You can take n over 2, n over 2 minus 1. It doesn't change. You have exactly the same picture. So what is this guy here? This guy here is this one. Right? And so if you think about what it means, well, you have all your electrons, all the electrons occupy all the orbitals starting from the center up to a given angular momentum. So if I plot what's going on, like the density profile, I will get something like this, where the density is the same, the bulk of the system. So this is R, this is the radius. So imagine if you plot this wave function, but the density of this wave function in real space, it's like a droplet, centered at the origin.
Yeah, but this is very specific for the non-interaction quantum program. If you plot the same picture for fractional, there will be it looks different. There's something called overshoot on the edge.
Yeah, sure. I mean, I don't just give you some insight why this should be. Here you're probing edge excitation of your system. Physically, if you look at the eigenstates of the region-density matrix corresponding to this eigenvalue, this is like the integer quantum Mole effect, but for a smaller system size. Basically, it's a droplet living in A with the density nu equal to 1 if you properly choose your NA. Right? So this is like a small droplet. And then, of course, when you look at what's going on here, the eigenstate of this guy here is like the bulk plus like a small excitation at the edge, and so on. So the wave function, the eigenstates of the region-density matrix, actually this is our bulk wave function. They are not edge wave function. They are true bulk wave function, but bulk plus edge excitation. So from that point of view, it's not too surprising that what you observe here is also the energy spectrum for the edge state. So when you cut, well, the first thing, the lower excitation that you, well, the most important weight will be just like the same state, plus some oscillation, more and more oscillations. And of course, the weight of these oscillations will just vanish, which means that the weight in the region-density matrix should decrease, which means that the levels, the energy of the level should shoot up in energy.
So it's not about the increases, the same picture should be related.
Exactly the same picture will be true for the interacting system, and I will show you that in 10 minutes.
What do you get if you do the calculation for a state that's 1 minus 1/3? Where the edge is more complicated.
So in that case, if you look at 2/3 state, you will have, for the entanglement spectrum, you have signature of two edges, the edges of the minus 1/3 and the edge of the nu equal 1, two counter-propagating edge state.
So you see that in the entanglement spectrum?
The entanglement spectrum, the real space entanglement spectrum, not the orbital one. If you know the story, the orbital one is just flipping the spectrum when you do the particle conjugation. So really keep this information in mind. So the first message here, when you do the entanglement spectrum, just properly select your quantum numbers and plot your data, let's say per sector first. I think that's one of the, if you talk to Haldane, and when he talks about the story of the entanglement spectrum, he said that at the beginning there was like, he saw nothing. It's like a bunch of data and no specific structure there. But as soon as he has plotted he has focused on a single block of the reductivity matrix by fixing the number of particles, by having decided that, well, if I cut my system, basically, I should look at the number of particles that correspond to the filling factor of the original state. And so he had, like, much less data. And of course, well, LZ is a good quantum number, so plot as a function of LZ. And then you see the edge mode appearing automatically. And it was for an interacting system, not for a non-interacting one. So really, if you want to play with all this business of entanglement spectrum, really think about the quantum numbers and how you should display your data. It's really important to see the structure imagine. Be guided by what is the physical picture once you cut your system. The physical picture here is you should get exactly the same state up to some edge excitation. Okay, so now I will switch to another non-interacting case, which is the case of topological insulators. So you can ask me, okay, it's a nice calculation. So you claim that for topological state, you observe the edge modes inside the entanglement spectrum. But you pick the only example where it's how you can drive your system away from a topological phase when you have the integer quantum Hall effect with only a single Landau level. Well, it's not really easy without breaking some nice symmetries like the LZ and adding some disorder. Okay. So in the lecture notes, you will have one section about topological insulators and how you compute the entanglement spectrum for topological insulators. I don't want to spend too much time on that, so I will just show you some results on this, but look at the notes and you will get much more information. So what I want to convince you here is that if you do the entanglement spectrum for a trivial phase or topological phase, you don't get the same result. This one, nah. Oops. Is it okay, or should I turn off the light? Okay. So I won't talk about all the topological insulators. The simplest thing that you can imagine. Take the chain insulator. So the chain insulator, if you don't remember, it's like the integer quantum Hall effect, but with a zero magnetic field. That's the Haldane model from '88. We have I don't know how many models on the market. Take the one that you prefer. This is the two-orbital model proposed by Bernevik, Hughes, and Zhang. And you can tune the mass parameter, so you can drive the system from a topological phase to a trivial phase. If m is bigger or smaller than -2 or smaller than -2, you get a trivial phase. If m is between -2 and 2, you get a topological phase. Put the system on a cylinder. So this is my lattice. I got 2 orbitals per side, square lattice. And of course, if you look at the energy spectrum on a lattice, if you're in the topological phase, well, you have the conduction band, the valence bands, and you have the 2 edge modes, one at each end of your cylinder, counter-propagating. So if you look as a function of, so kx is the momentum along the perimeter of my cylinder. This is the energy. You get the blue edge mode, this one, and the red edge mode, this one. If you drive the system to a trivial phase, you don't have any edge mode anymore. So, like in the same way, we have done the calculation for the integer quantum Hall effect. All the topological insulator, all the lattice models, you can do exactly the same kind of exercise where you take your creation operator, C dagger, you decompose into A and B. Remember that it's always simple to write down the ground state of your system where you completely fill one band. Let's say when you completely fill the conduction band here. It's quite simple. It's just the product of all the orbitals of the conduction band. Now, of course, if you want to write this wave function in real space, it's quite a mess because you have diagonalized the Bloch Hamiltonian, and going back to real space is actually quite difficult in principle. But still, it will be exactly the same kind of calculation that we have done here. Fortunately, when you deal with a non-interacting system, there is one more thing that you can do. Here, I've shown you how to get the entanglement spectrum. And what you get as the entanglement spectrum, or more precisely what you have written down, is that the reduced density matrix, you write it as an exponential of some entanglement Hamiltonian. So, the question is, what is this guy here? Well, for a non-interacting system, actually, you can show that this guy can be written as a one-body Hamiltonian. More precisely, it's one-body Hamiltonian if your state is a single Slater determinant. So as long as your system is just single Slater determinant, which is the case for an occupied band, you can rewrite this guy as a one-body Hamiltonian. So it's like, in this picture here, you remember we built the many-body energy spectrum of the edge starting from the one-body energy spectrum. But actually, you can reverse the procedure and go from the many-body to the one-body spectrum. So you can do that for the entanglement spectrum too. And this is what you get. So imagine I start with my topological, my chain insulator in the non-trivial phase. Right? And what I will do is to cut my cylinder into two parts, A and B. I choose this way to cut my system into two because I want to preserve the rotation, the invariance, the rotation symmetry along the cylinder axis. So I have one good quantum number. Right? Now, if you do the calculation, you have to fix, of course you have the edge here, so you have to define your Fermi level. But it doesn't matter, actually. If you do the calculation, not for the many-body spectrum, but for the one-body spectrum, this is what you get for the topological state. You will find the analogous of a conduction band, a valence band, and one edge mode going from the conduction band to the valence band. If you drive your system now to a trivial phase just by increasing M, the edge mode will disappear. So yes, it makes a difference if you have a topological phase or not. The entanglement spectrum is sensitive to the fact that you're looking at topological phase or not. You see the edge mode, or you don't see it.
So, if I understand correctly, if I'm going to think in terms of these boxes, so we still have kind of, we can label, we have a good quantum number, so we can use it.
Yep.
But the wave functions that we have in this case are block wave functions once we solve the Hamiltonian. So, do I need to transform them according to the geometry that I need?
Yeah, you need to perform exactly what we have done. So each state, of course, when you don't, if you don't have the translation invariance in that direction, you have a bunch of state per kx value. But each of these states you can decompose onto a wave function that only lives in A and only lives in B, exactly like we have done for the calculation. Yeah.
So does the entanglement spectrum also indicate the topological sector? So in this case, if the bands were like J numbers -2 and +2, would they see two states in the entanglement spectrum?
Yeah. You will see. You have only. You see. It's like, remember the story of the AKRT model. The AKRT model. When we have computed the entanglement spectrum, we have made a choice. We said, okay, we freeze completely the edge excitation. So let's say the two spin 1/2 are up. So we took a single state. For here, it's exactly the same story. So when you define your Fermi level, you completely freeze the edge excitation. Okay? So you can forget about the edges that you have here. The edges, they don't contribute to the entanglement spectrum that you have here. So now when you cut, you have a single edge, which is the edge that you have created by cutting your system into two. So that's why you have a single edge mode, and not like the true energy spectrum. If you look previously, the true energy spectrum on a cylinder, you have, of course, the two edge mode, which is not the case for the entanglement spectrum. Yep.
Just so you have shown the situation for the two different sectors, one in the trivial sector and one in the topological place. What happens with the entanglement spectrum if you continuously change M over the transition?
Well, at some point you have a problem to define what is the conduction band. You have a singularity. Your two band will touch. So what is the definition in that case of a field?
If you use the projector
here? But it will be Hill defined exactly at the degeneracy point. So you can go slightly before the transition or slightly before, slightly after. This will work. But just at the point there is.
So I mean, the spectrum will always look the same if you're just slightly below?
No, I mean, you have to be really careful. I mean, once again, maybe I give you like a simplified picture of the story for this one. There's a more precise way to define, to detect the topological order in the entanglement spectrum for a non-interacting system, which is basically what's going on to the entanglement spectrum when you change the energy, the Fermi level. So some state will jump from the conduction band of the entanglement spectrum to the valence band. And this is where you detect that you have a topological state. If there is no state in the gap, you will see nothing happening to your entanglement spectrum.
So this is a difference with respect to the two-band structure, where you see something continuously changing and going to the closing of the gap. In the entanglement spectrum, so to say, you always fix it to 0, 1.
Yeah, but somehow you want to detect topological order, so it should be. I mean, if you go to interacting system, the situation is a bit more tricky because there you will have to define an entanglement gap that will close like continuously when you go through the transition.
Is it true that the entanglement Hamiltonian is adiabatically connected to the gap strings with the Hamiltonian? So that this is some sort of flat band equivalent?
Yeah.
So that basically this operation can be done only when you have a gap here, that structure.
Right. Okay, so now I have like 22 minutes, let's say, to talk about the interacting case. But somehow the story is roughly identical to the non-interacting one. It's more surprising somehow that it works, but it's the same story. Yep.
What did we get in, for example, K-meaning to the for an entanglement spectrum?
You will get like the true energy spectrum. Oh, that's neat. So, interacting case. So I think now you know by heart the laughing wave function. So well, to be honest, mostly fractional quantum Hall effect and entanglement spectrum. So let me briefly remind you the bulk and edge excitation. Of the Laufin state. So the Laufin state looks like the wave function for the integer quantum Hall effect, except there's a power 3, which is quite a big difference. And now if you want to create bulk excitation for your Laughlin state, the simplest, the way to do that is actually to insert or remove flux quanta from your system. If you insert one flux, you will create one quasi-Hall excitation. So if you want like a naive picture of, or more naive, but a more pictorial way to represent that, so that's the density profile. So remember we use symmetric gauge, so everything is like a disk or a droplet. This is the radius. As you said, you have like small oscillation at the edge, even for the ground state. This corresponds to the filling factor, nu equal 1/3. And once you insert one flux, let's say at the origin of your system, so +1 quasi-Hall, what you do is you will deplete locally your system. So you will have now like this, and the density will go to 0 if you, let's say, you insert one flux at the origin. This is what you get. It's quite simple to write down the wave function for one quasi-Hall. Actually, it's quite simple to write down the wave function for any number of quasi-Halls. It's much more tricky when you want to do that for quasi-electron, where you remove one flux quantum from your system. But here, basically, it's just the product for Zi. It's the position, eta is the position of the quasi-Hall. All the particles times the Laughlin state. So that's the Laughlin state plus one quasi-Hall. If you want to understand, yep.
Sorry, what's the little squiggle?
That's one flux.
Okay.
One flux. That's fine. Well, one flux quantum. If I want to be like super annoying, I would say quantum. So how do you understand that? Well, remember that it's a polynomial. The one-body wave function is just Zm times the Gaussian weight. So if you multiply by Z, you change m to m plus 1. But now if you think about if you look in real space, these wave functions, remember they are like rings. So this is the m equal to 0. There is a ring for m equal to 1. There's another ring at m equal to 2. N equal to 3. And as Joël said yesterday, the radius of the ring goes like the square root of m. Right? So when you multiply by Z, if the particle is here in the orbital 0, it will go to the orbital 1. And so on. So that's why this picture here, imagine that you put eta to 0. What you do by multiplying by all these Zi, you take all the particles and you put them like one orbital. You increase the angular momentum of each particle by 1 unit. So you increase the size of your droplet like this by 1 unit. But of course, at the center, now there is no more particle. And if you do the plot of the density profile, you will see that the density will go to 0. And you can even compute the size of the quasi-Hall this way. Many quasi-Halls. I won't write all the wave functions. You have many of them. The point is, when you have many quasi-Halls, for a given number of particles, there is a well-defined number of wave function. My point is the following. Adding quasi-holes, it's like, if you put them all at the same place, it's like creating a hole into your system. Remember, Laughlin state is a true topological phase. A true topological phase. So when you add holes into your system, it's like changing the genus of the surface. So there is some non-trivial things going on. So all the story of adding like many quasi-holes, for each number of quasi-holes that you add for a given number of particles, there is a well-defined number of wave function that you can write down. And in the same way, the counting, the 1, 1, 2, 3, 5 counting was the signature of the chiral edge state. The counting that you have here is the signature of the Laughlin state. If you can characterize completely what's going on when you add, for any number of particles and any number of quasi-holes, how many states you have, it's like fingerprint of the Laughlin wave function, of the Laughlin phase, sorry. Okay? 10 minutes. Oh, perfect. Edge excitations. So, I think that Joel will talk about it tomorrow. So, the edge excitation of the Laughlin state, it's also Luttinger liquid. Of course, it's a directing system, but somehow in terms of how the spectrum looks like, it's exactly the same story that I've talked about for the integer quantum Hall effect. That's the edge. Rotation for filling factor 1/3. So this is the momentum K, this is the energy. The only difference here is that you can think about having a filling factor 1/3 also for your edge, for the edge of your system. So it's like a natural generalization of the Pauli principle. The Pauli principle tells you that you cannot have two particles at the same place. The Haldane exclusion principle say that for this system, what you have to think about is like bigger objects where you have one electron for 3 orbitals, and you cannot have more than one electron in 3 consecutive orbitals. So say that one particle in 3 consecutive orbitals. Yeah.
Is there a quantity through these calculations that can help us like give a topological classification for the system that we have? For example, like an equivalent to the Z2 through the calculations that we have here. Like, for example.
Well, once again, this counting you can think about like a partition function for your system. If you know the number of quasi-holes, it's like having a partition function in terms of statistical mechanics. So once again, it's a way to identify your state. So it's clearly a way to, not to classify them, but at least to identify them just by the counting. Or you can relate that to the CFT if you're related to the wave function. It also tell you which CFT you have to look at. The entanglement spectrum actually is a way to extract information about the CFT if your state can be written as a CFT correlator. Okay, so now we can do exactly the same kind of exercise that we have done here using this principle. It's an exercise, and you will see that you will get exactly the same counting. So far, so good. How to do the entanglement spectrum for the system? Well, if you want to do the real space entanglement spectrum, it's the same calculation, except that here the wave function is not a single Slater determinant. It's a sum over an exponential number of Slater determinants. So the only way I know how to do the calculation, well, actually I know 2 ways. The first one, if I know the decomposition of my state on the occupation basis, I can do the exercise I've done for every Slater determinant, every state of my occupation basis, and compute the Schmidt decomposition numerically. Some people have also done the calculation directly for the real space cuts using the real space expression of the Laughlin state. It works too. You get the real space Kalman spectrum. And now, come on. Okay, good. If you remember what I've told you last time, if you look at the integer quantum Hall effect, written as a single slitted determinant, so the product of it's a product of all the creation operator for all the orbitals. So you can cut it in the orbital space. You say, okay, the part A is going to be all the momenta from, let's say, 1 to 4. And the part B will be all the orbitals from 5 to 9. Well, say 8, since I use the same notation. It's just a way to cut my system into two. Here I cut in momentum space, or in orbital space, not in real space. But it's another way. So what kind of information do I get from this way of cutting my system into two? Well, the integer quantum Hall effect, you get nothing, because basically this is a product state in this basis. So you've got this state for A, tensor product, this. So the entanglement spectrum is trivial. Single non-zero eigenvalue. You don't see any specific signature. Now, the story changes a lot when you look at the fractional quantum Hall effect or a strong interacting system, because there you will have to decompose onto an exponential number of these occupation states. So actually, the orbital entanglement spectrum, which was originally proposed by Lee and Haldane, the first paper about the entanglement spectrum is about the orbital cut. For the interacting system, give you some non-trivial information. And this is what you get. So if you do the real space cut, or the orbital cut for the Laughlin 1/3, you will get roughly the same information. If you look what's going on as a function of LZA, so once again, I've picked a very specific value of NA. I said like NA equal to N over 2. And this is what I observe. So now if I look at the smallest LZ that I can create, I have one state, then another 1, 2, 3, 5, 6, 7, 11, and so on. You get the U1 counting. If you're able to do the calculation for a very large system, you will also recover the slope. Well, you will recover the linear dispersion relation of the H mode. So it works the same way for the interacting case. Actually, it's even better than that. The integer quantum Hall effect, if you look carefully at the calculation, the counting that you have, the 1, 1, 2, 3, 5 counting, there is no options, actually. Because for each specific value of NA and LZA, there is a given number of states that you can write down, given number of configuration, and these are exactly the configuration of the counting of the H mode. But now, when you look at the interacting case, if you take a random state, you have much more levels. This is exactly the same filling factor, the same number of particles, the same way to cut your system. So as you can see, if going from here to there is like an exponential reduction of the number of levels in your entanglement spectrum for the Laughlin state. If you remember the story of the AKRT model versus the Heisenberg model, or at least the AKRT model, what I've said is basically as soon as you have an exponential reduction of the number of levels in your entanglement spectrum, it means that you can write down a matrix product state, a good matrix product state for your model state. And this is exactly what happened for what is happening for the Laughlin state. So actually this state is not completely random. You take the Coulomb interaction, you project it onto the lowest Landau level, and you set the filling factor to be equal to 1/3. So we know that the Laughlin state is a very good approximation of what's going on at 1/3, including very good approximation of the true ground state, of the ground state of the Coulomb interaction at the same filling factor. And what you observe in the entanglement spectrum is a pattern that corresponds exactly to the one of the Laughlin state, with exactly the same counting, the 1, 1, 2, 3, 5. And like for the Heisenberg model, remember the Heisenberg model? We had the two states corresponding to the Eckert model, entanglement gap, and then higher energy levels. So it's exactly the same story for the Coulomb interaction. The bonus thing here is actually it's not really random. As you can see, you have many structures emerging here in the entanglement spectrum. One way to think about the entanglement spectrum of the Coulomb ground state is to say, well, this is the entanglement spectrum of the Laughlin state, plus, on top of that, some excitation above the Laughlin state. So actually, what you extract here is information about the neutral excitation above the Laughlin state, not by looking at the Laughlin state itself, but at looking at a model which is a little bit away from the exact Laughlin wave function, but still pretty close. The last thing I want to show you, I've told you right now two ways to probe your interacting system. The real space cut. I didn't give any details here, but it's exactly the same kind of calculation that we have done for the integer quantum Hall effect. The orbital cut, where you cut directly the orbital space, which is quite convenient because if you write a code, this is exactly what you have for free. But there is another way to cut the system, and you will get another kind of information about about the excitation. And actually, if you look at the textbook about reduced density matrix, like a book about introduction to quantum mechanics, the usual way it's defined is the following. What I will do is to take the reduced density matrix. I will look at NA particles, prime NA, and you integrate over x NA plus 1, n, and here is 1, xNA, xNA plus 1, xn times this. The prime is here, and here there is no prime. So basically what I do is just to integrate over NB particles. So I define NB as n minus NA. And I trace out over NB particles in my system. That's the usual definition, actually, for a reduced density matrix, like the two-particle density matrix from an n-body system. It's just you integrate over all the particles except two. Right? So this way of cutting the system into two does not involve any cut in real space, not even an approximate one like the orbital. I don't change the geometry at all. What I do is just to remove some particles from the system. So what kind of information do you get? So you don't change the geometry. If you don't change the geometry, what you get is information about the bulk excitation. So here I will cheat a little bit. The calculation is on the torus because it's pretty neat on the torus. It also works pretty well on the sphere, but I have the zeta for the torus. Start with the Laughlin state on a torus. It's threefold degenerate, but actually it's not a problem to compute the entanglement spectrum. And you count how many states you have per momentum sector or per angular momentum. And this number is exactly the number that is predicted where if you have NA particles in your system and the same geometry that the original bulk wave function, which is defined for a given number of flux quanta, n phi, and a given number of particles, n. So what you probe with this particle entanglement spectrum is the bulk excitation of your system. It's more than the counting of how many quasi-Hall states I can generate. The wave function, if you compute the eigenstate of the reduced density matrix for this problem here, the wave function are the quasi-Hall states. They are not random, they are the quasi-Hall state. So starting from this bulk wave function, by removing particle, I can access bulk excitation, not only counting, but I can get access to the wave function themselves. Well, same story. If you move away from the model state, you go to the exact ground state of the Coulomb interaction, same filling factor, same number of particles. You observe a low energy structure that is roughly identical to the Laughlin state, a large entanglement gap, and a high energy state. So it's exactly the same story that we had for the IKLT model. All in all, I think just to summarize all this business of entanglement spectrum, it's a really nice tool to extract information about the excitation of your system for topological phases. It's a bit more than that, actually. Even for some, like if you think about the superconductor, for example, or Bose-Einstein condensate, you can extract information, of course, from the reduced density matrix. Nothing surprising. People know that for a long time to probe condensation, for example. But here it's very nice for these topological phases because it gives you like a tool when you start from the ground state wave function of a bulk, and you have tons of information. And not only information, but a way to characterize the system. If you want to do that for whatever topological phase, remember that there is not a single way to catch a system. You can cut it in real space, you can cut it in momentum space, you can cut it in number of particle space. All of them might provide different information. The integer quantum Hall effect is trivial when you cut it in orbital space. It's non-trivial when you cut it in real space. For interacting system like this one, it's not trivial neither for the orbital or for the real space. And the last point is when you have like tons of data, like you have a huge pile of numbers, sort them. Have quantum numbers to have labels for each of these numbers, and you will see some structure emerging. Okay. Yep.
Sorry, what's the difference that entanglement gap is much bigger than one, or?
The gap here, the entanglement spectrum gap? Well, the claim is the same as the claim we have made for the IKLT model and the Heisenberg model. If you move away from the IKLT Hamiltonian, like if you take the Heisenberg Hamiltonian, you observe entanglement gap. The claim is that if this gap stays finite when you take a large system size, somehow the physical property of your system should be, or the universal property should be defined by the low energy structure that you observe in the entanglement spectrum, with the structure which is below this entanglement gap. It doesn't have to be 1, right? It will scale with the system size. For most of the point, like the Heisenberg model, you can compute what is the value of the entanglement gap when you have a very large system size because you can do de-energy. It's not possible to do that for the fractional quantum Hall state. But the hope is that, or at least what the numerics points out is that, well, this should at least stay finite when you go to a very large number of particles. But it's not like just 1. It can be 0.8 or whatever. So it's actually one of the things we don't understand now for the entanglement spectrum. Like, if you ask me a gap you think about an energy scale. So I know my system is protecting as long as the gap is that. If I, let's say, crank up the temperature, if the temperature is smaller than the gap, then nothing will happen. It's much more difficult to quantify what's going on for the entanglement gap. Yep.
So if I have an arbitrary correlated state that I see that it has an entanglement gap, can the entanglement spectrum somehow help me to identify the relevant reduced Hamiltonian that will give me only the states below, like the relevant?
Sometimes it can help you to guess what is the physics of the system, of the model state. Maybe we can talk about that, but in some cases you count how many states you have, and just by, but wait, this number is rated, for example, the number of dimers I have in my model. So, like a simple way. So maybe that is a simple way to understand what's going on in this low energy structure. So it's also a guide to say, okay, this phase should be close to this one. Yep.
So what sort of light excitations does it tell us about? Like these quasi-Hall excitations?
Here, all the quasi-Hall excitation, because imagine that for a given number of particles, if you fix the filling factor, like 1/3, there is a given number of flux quanta. Now, if you remove particles and you keep N5 fixed, it's like having Na particles, but not the number of flux quanta corresponding to 3 times Na, but much bigger number of flux quanta. So it's the original like the Laughlin state for Na particles, but like with 10,000 flux quasi-Hall in your system.
So these next gaps that we see there is the higher fraction size.
This corresponds to the exclusion principle. So maybe what's going on is like this state is related to the clustering properties. All the wave function vanishes when you put 2 particles in the same spot. So you can relax this constraint a little bit in terms of exclusion principle, and the other gaps are related to, okay, I can put here, basically the information about quasi-Halls is I cannot put more than 1 particle in 3 consecutive orbitals. So the weaker version is like I cannot put 1 particle in 2 consecutive orbitals. And this is the gap that you observe right here in the system. If you know FCI, it's exactly what you see. It's like super nice. Yep. Yeah, so it works pretty well. If you start with the bulk, well, you have to be careful, because in terms of CFT, you have to get all the topological sectors. So if you take the Moritz state, if I work on the sphere, for example, and take only the ground state, I don't have all the topological sectors. But still, by cutting in 2 different ways, for example, even this one, you get 2 of the sectors, like the vacuum and the psi. If you want to get the sector corresponding to the sigma field, you need to have like 1 quasi-Hall here and 1 quasi-Hall here on the sphere, and then the entanglement spectrum will give you the CFT counting for how many descendants you have from the sigma field.
So can you think of it as a proof that every topological state, that the topological phase has a CFT on the boundary?
It's a bit more tricky. For example, if you think about the story of the 2/3 state, it's a bit more difficult to extract the information about the edges, because once you have 2 counter-propagating edge modes, of course the spectrum will combine, right? So you have one mode going in that direction, the other one going in that direction. Well, the energy spectrum is like a diamond, so it's sometimes not that easy to track how many states you have for one mode and the other. At least in finite size numerics, yes. Once all these numerical tools, we have to be honest about the limits of what we can do. For some systems, it's much more difficult to extract this information. Of course, all the state that you build from CFT, it's like immediately you get all the information. Yep.
You have a reference where the quantum Hall state thing was done in more detail.
The quantum Hall state, or the MPS, or just generic?
Well, this is some notes for a senior. I would like to go through it. If I have some lecture notes or something, that would be great.
I can give you the preliminary lecture notes if you want, with all the details, or I can give you some references for like articles about all this business. So, yeah, the reference will be better. That's yeah. I think it's time for the apéro, right? Apéro?